All right. All right, let's do 4.2, least squares regression. This will be the last section of chapter 4, as well as the last section of our first unit. After this, we'll get into a review, and then we'll have an exam over the first 4 chapters. That will be our first major exam. So let's talk about least squares regression. When you were in elementary school, middle school, maybe you did this some in Algebra 1 and geometry, you were asked to come up with a line of best fit. And your teacher may have had different suggestions on how you come up with that line of best fit. Maybe you always start with a point and then you kind of draw a line from one point through the rest of them. There's a bunch of different ways. Mathematically, what we're going to be doing is finding the line of best fit, not an approximation, not an estimate, but the actual line of best fit based on our way of measuring things. And that is the least squares regression line. And so what it does is it looks at a line and then it measures the distance, the vertical distance from that line to any given point. And the least squares regression line minimizes that total distance. So again, imagine we have our scatter plot. It's going to draw an imaginary line through that scatter plot, and that line is going to minimize the vertical distance from all of the points. And there's only one line that does that. And I'll actually go through and show you how we can put that line in our graph. So get out of this, go back to our stat calc, and we're going to go into number 4, our linear regression line. So we have our X list, we have our Y list. What I'm going to do now is come down to here where it says store, and that's regression equation. So I can choose to put that regression equation into one of the variables for my graph. And the process, the steps for it are not super complicated, but there's a few of them. So pay attention, or you can rewind if you want to do this. But you go to vars, our Y variable, we're going to choose function, and then I'm just going to choose Y1. So that means once it comes up with my linear regression equation, it's going to plug it into Y1. So I hit enter, calculate, and we already saw this. This is where we figured out what our R value was. But now it put an equation in for Y1. Now when I graph, that blue line is our least squares regression line, meaning of all possible lines that could possibly be drawn, this one, if you add up all of those vertical distances, this line has the smallest sum of those distances. That's what our least squares regression line does. And as the name implies, it does square that distance. Again, same idea as our standard deviation. It doesn't want a distance above and the distance below to cancel out. So it squares them, so it gives us all positive numbers, so they just add on to each other. Once we come up with that, it can be used for 2 different purposes. One, it can be used to estimate an average of the Y value at any specified X. And 2, it can be used to predict the value of a Y for an individual given that X value. So we can use it as simply going through and looking at this line and saying, okay, well, at this X value, the average Y is going to be where this comes out. This line gives us an average Y value based on an X value. And so we can either pick an X value at random and figure out what the Y value should be, or we can figure out, determine someone's X, and then based on that, we could predict what their Y should be. So it's a line. And so like all lines, we have Y equals MX plus B. And if you go into our calculator, that's what this linreg looks like, ax plus b. Instead of mx plus b, they use a as the slope instead of m, but that's the form that they give us our linear regression in. So if we scroll all the way back down and we calculate again, a is our slope, b is our y-intercept. Now, you see that instead of y equals for our regression line, they've changed that variable. It is no longer y, it is now y hat. And the variable y hat tells us that the answer we're getting is a prediction. It is an estimate using a line of regression. If you have y equals, y is something that you had to observe. Y hat is something that you are predicting. So that's the difference, and it's important to make sure that you use that y hat and not just y. And then it gives us formulas on how we can find both the slope and the y-intercept of our regression line. We do not have to do any of that by hand. We'll be using our calculator to find our slope and our y-intercept. So those formulas are interesting, but we will never actually have to use those formulas to calculate our regression line. This goes through and tells you how to find that. It's the same it's essentially the exact same steps to find our R, because our R and the A and the B are found in that same function, that linear regression function. All right. Here we have a couple of different questions. Go ahead and answer these first two parts. So the first one, you're asked to find the least squares regression line. And for the second one, we're looking to see if our R value, and using table 2, lets us say that there is in fact a linear relationship. So pause your video and attempt to come up with your least squares regression line. So plug in the x's into L1, y's into L2, and then do that linear regression and come up with the equation. And then the same thing for part A, but instead of writing the equation, we're just looking for the R value to begin with. All right, so let's do this first one. So edit, I'm gonna go up, I'm gonna clear my two lists. I'm gonna enter the data. So we have 1, 2, 3. So 1, 2, 3, 4, 5, and then over here, three, 5, 9, 13, 15. Stat, calc, number 4, list 1, list 2, and then we're going to calculate. And the parts I care about here for this question are the A and the B. A is my slope. So as I'm rewriting this, it's y hat equals, because I'm predicting, and then it's 3.2x, and then minus the y-intercept, which in this case is negative 0.6. So that's why it's minus 0.6. And that's an equation that will allow me to predict a y value given an x value. All right, on this next one, the first thing we needed to do is find our R value to determine if a linear regression line would work. If there's not a linear relationship, then linear regression isn't the appropriate regression model. So the first thing we do is I find my R value, negative 0.95. Then I have to remember, okay, well, in order to find if a linear relationship exists, I have to check the absolute value of my R against a critical value. So the absolute value is 0.95. My N, my sample size here is 5. I have 5 different data points. Then I can go into my table and see, okay, well, if I have a R value or a sample size of 5 and N of 5, then my critical value is 878. So yes, based on my R value, there does exist a linear relationship. Next, it says find the least squares regression line. So in order to do that, I've already done all of the work. I just used the R part for part A. Now I'm going to use the A and the B part in order to answer this question here. And so again, y hat equals negative 2.167 x plus 18.667. Now it says use this equation to find y hat if x equals 6. So what is the expected output when the input is 6? So in order to find that, y hat equals negative 2.167 times 6. That's what x was. And then plus my 18.667. And I get a predicted y value of 5.667, 5.668. So that means if x is equal to 6, I expect y to equal 5.668. It may not equal that in real life, but that would be my estimate. That would be my guess. And next, it asks me to find the difference between what actually happened when I put in 6 and what my prediction was when I put in 6. So when x equals 6, y hat is 5.668. That's the calculation I just did. Now, when x is 6, y equals 6. And I know that because of this point here. That is an actual observed data point where x was 6 and y was 6. So that's an observation. That's why y equals 6. Y hat, my prediction, is what I get when I plug it into my equation. Y is what I actually observe. Now, in this case, I didn't actually observe it, but it was given to me. So I treat that as an observation. And then it wants to know the difference between those two values. And so that difference, the difference between y and y hat is called a residual. And it is the error in my prediction. And we find it by doing y minus y hat. So 6 minus 5.668 gives me an answer of 0.335. So my residual is a positive number, which means my observation was greater than my prediction. Now, again, residuals, much like a z-score, isn't good or bad. Having a positive residual is not good or bad. Having a negative is not good or bad. It's all dependent on the situation. If you are trying to predict a time, so your input is, let's say, how far you're running, and your output is the amount of time you predict it will take, then having a positive regression or a positive residual is bad. If you predict running 3 miles will take 1 hour, and then it turns out in your observation, running 3 miles actually took you 1 hour and 10 minutes, that's not good. You want to run faster typically, and so having a positive residual is bad. But in another category, having a positive residual might be better. Maybe it's age and how much weight you can squat. So having a positive residual means you can squat more than people would think, or that would be predicted, which typically means that's a good thing because you want to lift more weight. So again, a residual is just saying whether it's above or below the prediction, and that is not necessarily a good or bad thing. It depends on the setup. This goes into more about residuals, and then it gives us 2 examples. So it talks about how far away someone can see a highway sign, and it gives the actual distance that they could see it at, and it wants us to find the predicted distance and then determine the residual based off of that. So go ahead, do those two calculations, find the two predicted distances, and then the residuals for both of those, and then we'll go over it together. So here, you 577 minus 3 times 18, which is our x, and we end up with 523. I'm going to assume that is feet. It doesn't really tell us. That seems like a reasonable unit. And then we do 510, the observed x minus the predicted, or sorry, the observed y minus the predicted y, and we get an answer of negative 13. That means this 18-year-old's eyesight is worse than predicted. A common way you see this kind of idea of predicted versus actual is in eye exams. If you go and get your eyes tested, or if you've ever done that, and you come out and they say, oh, your eyesight is 20/20, or it's 20/10 or 10/20. What that's saying is where you actually see something versus where you should see it. So eyesight of 20/20 means you see it 20 feet, what they expect you to see at 20 feet. If you're at 10/20, that means you have to be at 10 feet where the average person has to be at 20 feet. I believe that's the way that goes. And then if you're something like 40/20, that means you can be 40 feet away from something and still see it, while they would predict it takes the average person being 20 feet away. And so it is a similar type of setup. They're not actually looking at the residual, but they're telling you the prediction and the observation and putting those together so that you can kind of understand where your eyesight is compared to average. And so that's what eyesight charts are for. Like if you have 10/20 or 40/20, that 20, that second part, I believe, is what the average is or the prediction is. All right, and then this next one, same thing, 577 minus 3 times 20, and that gives us 517. 590 minus 517, and it gives us a residual of positive 73. So this 20-year-old's eyesight is very good. In this case, they're 73 feet further away and they can still see the sign. And so they have much better than predicted eyesight. All right, so this problem kind of incorporates everything all together. If you pause this video and attempt or work on all 3 parts. So you have to calculate the R. You have to come up and determine if there is a linear association between these. So you have to check your table. You have to come up with our y hat equation, our least squares regression line, come up with a prediction, and then find the residual. In order to do that, you have to put all of this data into a calculator. So pause this video, go ahead, enter all of that data, answer those questions, then come back and we will go over all of the answers together. All right, so for the first part, R is equal to negative 8 or 0.868. So our check is absolute value of R is greater than our critical value. So 0.868. And then we use our table and we use the fact that there are 21 data points. So our sample size is 21. So we'd go down to the 21 or 21st row in our chart and then go over, and that gives us a critical value of 0.432, or sorry, 0.433. And so there is a negative linear association. So now that we know there is a linear association, we can find that least squares regression line. And again, it always uses that y hat. It's going to be in the same function, the same way we found R. That's also going to give us our A and our B, which is our slope and our y-intercept. So negative 49.9 negative 49.495 x plus 3169.648. Now, all of this data was age of a mother, birth weight of a baby. And so it wants us to predict the birth weight of a baby if the mother is 27 years old. So 27, that's our x value. So y hat equals negative 49. So our prediction for a 27-year-old mother's baby's birth weight would be 1,833.285 grams. That's what our expectation would be. Now it says find the residual for that value. So that means we have to have y minus y hat. In order to find the residual, we have to have a data point with that x value. So we need to go through our list and see if we have any data points where the mother's age was actually 27. So we scroll through. Oh, we did have a 27-year-old mother. And so we have an observation for the birth weight. So our y value was 1588. Our y hat value was 1833.285. And we find the residual. And our residual is approximately negative 245 grams, which means the observation we had was actually below our predicted birth weight. Now, a common question is, what if we had multiple data points from 27-year-olds? Well, then you'd have multiple residuals. So let's say we had 2 women that were 27, then we would have 2 different residuals, and you'd have to find both of those residuals. All right. The last part of this chapter is talking about what the 2 components of our line tell us. So what does the slope tell us and how can we use it to increase our understanding? And then what about the y-intercept? So first, the slope. The slope always tells us something important. It tells us the predicted y value when x is 0, but it also tells us how increasing our x by 1 unit will affect our y. So if we look at our slope here, which is negative 49.495, so we can round it to negative 49 just for the ease of conversation. What that says is for every year the mother gets older, the baby's predicted birth weight will decrease by 49.5 grams. So if we would predict a 20-year-old to have an 1,800 gram baby, we would expect a 21-year-old to have a baby that weighs 1,750 grams. So every time they get 1 year older, we would predict the baby's weight decreases by about 50 based on the slope. So that's what slope is. And that is always going to be the case. It tells us how our y is going to change based on a 1 unit change in x. Now, our y-intercept. Our y-intercept can be useful and it can be not useful. So slope, always useful. Slope, always useful. Y-intercept, not always useful. It is more common that it is just necessary to be able to graph our line than it's actually going to be a useful piece of information. In the example that we just did, our y-intercept is 3169. In order to have a baby be predicted to weigh 3,169 grams when it's born, how old would the mother have to be? Well, in order for our y-intercept to come into play, our x value has to be 0. Is it possible for a 0-year-old to give birth? No, because a 0-year-old isn't alive yet and can't give birth that young, even if they were barely alive. So your y-intercept doesn't necessarily provide any useful information in a situation. In this case, it doesn't make sense because someone can't be 0 years old. In other cases, if we were to talk about how long it took to drill into the earth, let's say X was how many feet into earth we were going to drill, or how long it would take to drill 10 feet given a starting depth, well, then 0 would make sense. 0 feet would mean you're starting on the surface. How long would it take to drill from the surface of the earth down 10 feet? That would make sense. That would be a useful number, but that depends on the situation. So be careful. Don't just assume the y-intercept provides meaningful, useful information. It may just be necessary to draw the line. Cool. And that is the end of chapter 4. If you have any questions, again, make sure you're using that homework help form to ask any questions or emailing me through my stat lab. And that is the end of chapter 4. We will start giving you guys the review and getting you prepped for the first exam after this.